Veena cannot read when she holds books closer than 100 centimeters. 100 centimeters from her eye. This is the distance from her eye. Name the defect and prescribe a lens of suitable power to correct that defect, given that the normal eye near point is 25 centimeters. So let's see what's given to us. Well, if this is Veena's eye, then it's given that she cannot read when she holds books closer than 100 centimeters. So if anything comes closer than 100 centimeters, she cannot see it clearly. That means if it's outside of 100 centimeters, farther away than 100 centimeters, she can see it. And I'm going to put a green over there saying that she can see any objects over here. But if there's any object within 100 centimeters, then she can't see it. So we'll put a red for that. So she can't see anything over here. And I'm only going to go until 25 centimeters because beyond 20, or closer than 25 centimeters, even a normal eye can't see it. So we don't have to worry about this region. It's only this region that Veena is unable to see, which a normal eye can, but Veena's eye cannot do it. So the first question is, what is this defect? Well, I want you to pause the video and think about what that defect is. Well, since she can see things which are far away, but she cannot see things which are close to her, she is far-sighted. So the defect over here is, let me write that down over here, far-sightedness, because she can see things which are far away. So far-sightedness, or the biological term is hypermetropia. I will not write that, it's not needed. So we got that, that's the defect. And now we need to prescribe a lens of suitable power to her so that she can correct that vision. Which means we're like the doctor over here and we have diagnosed her issue and we need to now correct it. So what lens should I put over here is the question. And what should be the power of that? At first we might be wondering, well, is it a converging lens or a diverging lens? What should we use? Well, we don't have to worry about that at all. So let's think about this. First of all, how do we define power? Well, in optics, we define power, P, as the reciprocal of the focal length. The reciprocal of the focal length. So we need to figure out what is the focal length of the lens that we're going to put over here. But how do we figure this out? Well, all we have to do is think in terms of objects and images, and then we can figure this out. Think of it this way. For a normal eye, this is the near point. All right. So let me just call it as, okay, let me just write. This is the near point for a normal eye. Right? Because beyond this, closer than this, a normal eye can't see things clearly. But for Veena, this is the near point. Because for her, closer than 100 centimeters, she can't see. So this is the near point for Veena. So near point for, I'm going to put a star over here saying that's a near point for Veena. So in order to correct her vision, she should be able to see all the way up to 25 centimeters. How do we do that? Well, another way of saying that is that if there's any object right at 25 centimeters, then its image must be formed at 100 centimeters. Does that make sense? Think about it. If the object is at 25 centimeters, and if the lens converts it, and the lens creates its image at 100 centimeters, then she will be able to see that. So this is our object. So this is the object, and this will be the image. So we need a lens which does this. So we know what the object distance is. We know what the image distance is. And so all we need to do now is the focal length of the lens needed. So it'll be a great idea now to pause the video and see if you can solve this yourself. All right, let's do that. So let's write that down. Object distance is given to us as 25 centimeters. We also know the image distance. The image distance is 100 centimeters. But we need to be careful. We have to use sign conventions. Since our lens is going to be over here in front of our eyes, we're going to choose the incident direction as positive. So this is going to be the incident direction. And all the distances, all the positions on the right side of the optic center is going to be positive. This side would be negative. So this will be negative. Object distance is negative because it's on this side. So this is negative 25 centimeters. Even the image distance is negative because on this side, in the opposite direction, right? So this will be minus 100. And so now we can go ahead and use the lens formula, because since we know u and v, we can calculate f. So let's make some room and let's calculate this. So the lens formula says 1 over f is 1 over v minus 1 over u. And so that gives us 1 over v. That's a negative 1 over 100 minus 1 over negative 25. Well, if you solve that, let's see what we get. You get 1 over, so negative 1 over 100 plus 1 over 25. Take 100 as common. You get minus 1 plus 4. That gives us 3 over 100. 3 over 100. So the focal length is the reverse of that, reciprocal of that. That's going to be 100 over 3. And we'll just keep it as it is. So this is the focal length. So this is so many centimeters. And notice, since we're getting a positive answer, this means the principal focus is on this side. So whatever lens we're going to use, its principal focus is on this side. And so now we can figure out whether it's a convex lens or a concave lens. Think about it. If the incident direction is, if you have an incident ray in this direction, which lens will give us the principal focus on this side? Well, it should be convex. Because if it's a concave lens, let me just quickly draw that. Then if the incident ray was somewhat like this, it would have diverged away, appearing to come from here, so the principal focus would have been negative. So it's a convex lens, and we found out its focal length. That's 100 over 3 centimeters, but we require power, and we can calculate that. So power would be just the reciprocal of this, so that's going to be 3 over 100 centimeters. But if you put this in the SI unit, because for power we always put things in the SI unit, that's going to be 3 over 100 centimeters is 1 meter. 1 meter. So 3 meter inverse, or 3 diopters. So the prescription that we give is, we say that she needs a lens which has a power of 3 diopters. The positive power itself is telling us it's a convex lens. So the beauty is, just by looking at these signs, we can figure out whether it's a convex or a concave lens. We really don't have to remember that for farsightedness we have to use a convex lens. It can be worked out directly.